Hello. With the growth of data sets in scientific computing, visualizing are more demanding. And a particular visualization tool that's often used is the contour plot. Because the contour plot not only tells you local extremum in the scalar field, but it also gives you information about how the field is changing, across a certain area in 2D or 3D. Also, for example, in the case of astronomy, when you have only two-dimensional information, for example, a sky projected image of something from a telescope, a contour plot can help you tease out 3D information when it's not available. So we focused on contour mapping in parallel, and the part of contour mapping that we focused on is determining what are the interesting contours to draw. For example, if you imagine these contours to be elevation of a mountain, if you only decide to draw these particular contours, you would miss the fact that there are actually 4 distinct peaks in this mountain range. So determining what are the interesting contours to draw is where we spent most of our focus. And that knowledge is contained in something that's called the contour tree, which contains information about the local extremum. And in order to determine that, you need to scan through all your data and essentially determine where are these local extremum. So that's where parallelism can come in.
And so the algorithm that we implemented, which we did not come up with, takes a sort of divide and conquer approach to doing this, sort of like a merge sort. So the contour tree for the entire box, to compute that, you compute it for the left half and the right half, and then there's a procedure for combining the trees at the end. And you continue that recursively until you get down to the point at which you're just working on 2x2 boxes, and then there's only a small number of possible trees. In 2D, it's 2, and in 3D, it's 4. So each one figures out what it is and sends the answer up. And to parallelize this, so at each step in the recursion, you spawn a couple of child processes. One takes the left half, one takes the right half. And you do that until some maximum number of threads is reached. And then after that, the algorithm continues in serial. And we ran our code on some cosmological data that we have, and we found that for small numbers of threads anyway, we're getting close to the ideal speed up.